right, today we're going to be doing an experiment on electron domain geometry. So the first thing that we're doing with the balloons we can talk about is the Vesper theory, which theorizes that electrons, both bonded and non-bonded, will repel against each other, and therefore we can predict the shape of a molecule. So the repulsion that they create around the central atom is going to tell us what shape they're going to take on, and we can predict the bond angles as well. So lone pair repulsion, so electrons that are non-bonded, so let's just use this one for example. If these ones are a non-bonded pair of electrons, and this is a non-bonded pair of electrons, that's going to have a greater repulsion over if this is a lone pair and this is a bonded pair of electrons. It's going to have, the lone pairs is going to have a greater repulsion than this one, and then that one is also going to have a greater repulsion than if this is bonded and this is bonded than that. So when we're going over the angles of this, there can be slight variances in that with the fact that bonded and non-bonded have different repulsions to each other. All right, so the balloons that we're going to be using and demonstrating with today represent our electrons, and the tie in the middle is going to be like our central atom, and these are going to either be lone pairs or bonded atoms. So the big difference between electron geometry, domain geometry, and molecular geometry is that the electron teaches us about the arrangement of different electron groups, including lone pairs of electrons and bonded and non-bonded, whereas molecular geometry does not include lone pairs, only the bonded electrons. So with the electron domain geometry, it includes the lone pairs of electrons and the bonded. The molecular geometry could be different if it's not including the electron pairs. So therefore, they will be the exact same shape when there is no unbonded electrons. So I think I wrote in here, yeah, on a few of them with my examples that they would be different if we were doing molecular geometry. So we're also going to be talking about the polarity of these examples, and the polarity is non-symmetrical distribution of electron density or uneven repelling of the angles. So, you know, polarity, if these are, we can kind of get into it more with this, but if they're unequally distributed, there's different bonds, distances between them. One of the atoms is more electronegative, and so it's pulling more. That's going to make it more polar, whereas non-polar is going to be an even distribution of charge over the whole molecule. No partial negative, partial positives anywhere in it. So we can start going through our shapes. So the first one that we have is linear, and it has 2 electron domains. It has no lone pairs of electrons. The bond angle is 180 degrees. My example was CO2, and it shows that, and there's no lone pairs. So this is going to be our linear molecule. So for triagonal planar, and this is going to be 3 electron domains, it could have 0 lone pairs of electrons, or it could have 1 lone pair of electrons. And that's just including, since we're including electron domain geometry, so it could have either and it would still work. So this is our example. So these bond angles are going to be 120 degrees from each other. My example was CO3 2 negative. I have it drawn right here, and I have it drawn with no lone pairs of electrons. And the overall charge is still 2 negative. I think the balloons do a really good job of almost showing repulsion and the bond angles, because with them being narrower and then getting fatter, they naturally want to repel and be as far away from each other as they can. So they naturally get into almost those shapes. All right, so the fourth one, tetrahedral. So it has 4 electron domains. It could have 0, 1, or 2 pairs of lone pairs of electrons. This is a tetrahedral shape. The bond angle between these is 109.5. As we can see, 1, 2, 3, 4. bonds or electrons coming off of it. My example was NH2 negative. So in this case, for that example, this tie would be the N. These two would be my H's, my hydrogens coming off of it, and then these two would represent actually the two lone pairs that we have coming off of it. This one is polar, and if this was molecular geometry, this one would not include these two pairs of electron clouds, and therefore this would be a bent or angular shape. So the other two were non-polar. I forgot to mention that, but that one is polar. All right, our next shape. The different color balloons don't mean anything. I just ran out of balloons. All right, so this has 5 electron domains, and this is triagonal bipyramidal. It could have numbers of lone pairs 0, 1, 2, or 3 pairs. This is a polar molecule. The bond angles in this one actually, it had it drawn out. The bond between this one and this one is 180 degrees. You're gonna have a bond between this one and this one that's gonna be 90 degrees. And then you're gonna have, similar to the triangular planar, you're gonna have a bond that's 120 degrees. So you are gonna have 3 different bond angles for this one. And I did ICl2 negative, and I have it drawn right here. You probably can't see it, so I have it drawn with the different angle groups, 90 degrees, 180, and there's the 120 degrees. I have the three pairs of lone pairs of electrons drawn in this one, and that's what 3 of these would represent, is lone pairs. Okay. All right, and then the last one, this is the octahedral. It has 6 electron domains. It can have lone pairs of 0, 1, or 2. The bond angles are 90 degrees on this one. I did SF6 as my example. So S would be this central tie, and all of these balloons would represent the bond to fluorine in all of these. And that one is also non-polar. So the only 2 that ended up being polar is the tetrahedral and the trigonal bipyramidal. Everything else was non-polar. And we went over the bond angles. So that is my examples of electron domain geometry.